This paper presents a novel skeleton-based technique for whole-body control of robotic manipulators using an adaptive image-based visual servoing law. Visual servoing is easily applied in practical settings where the end effector of the robot is not included. In existing literature, these algorithms have been applied to various tasks such as pick and place, boring, and object shaping, as seen in the video. These existing techniques identify features on the robot's end effector and assert control over the robot's task space. This causes configuration ambiguity in redundant robots. Moreover, occlusion of image features causes a failure in servoing. The proposed skeleton-based method uses morphological features that encode the entire configuration of the robot, thus preventing configuration ambiguity. This is done by using the skeleton of the robot. The skeleton is modeled as a constrained parametric curve. Specifically, we choose B-splines as our parametric curve and constrain their number of segments and order of each segment. Control points of the modeled curve are used to define the image error between the current and desired configurations of the robot as shown in equation 1. This image error is then used in our visual servoing scheme. We use an adaptive update law to estimate and update online a combined I-hand Jacobian JC hat for the system as shown in equation 2. Updates are performed by computing a model error which determines the difference between the current configuration and the expected configuration and projects it as a corrective term as shown in equation 3. A proportional image-based control law is used to derive the desired joint velocities for the robot using the estimated combined Jacobian as shown in equation 4. The data used for estimating this combined Jacobian is accumulated in a sliding window that is refreshed at each iteration of the control loop. The window size is determined experimentally. A small window size makes the system susceptible to noisy data and can cause sharp changes in velocity, whereas a window size that is too large makes the system prone to inefficiencies. We perform experiments in simulation and on a real robot, and compare the effectiveness of our skeleton-based adaptive image-based visual servoing method to traditional adaptive image-based visual servoing algorithms in literature. Images shown here represent the 2-link and 3-link planar robots used in our gazebo simulations. The proposed skeleton-based visual servoing method allows us to control the final configuration of the robot for a given target position. This is not possible using existing image-based visual servoing algorithms. This proof of concept video demonstrates control of a redundant robot without configuration space uncertainty. Again, this is not possible with traditional methods. We use the Franca Amica Panda robot for our hardware experiments. The green markers in the image show the different target positions used in the experiments. Our experimental results over 5 trials show both the proposed skeleton-based visual servoing and the traditional adaptive image-based visual servoing algorithms perform repeatably. When compared to a traditional adaptive visual servoing scheme, our proposed skeleton-based visual servoing algorithm converges faster with much lower overshoot. This can be confirmed by experimental results collected over 20 experiments. A robustness comparison is carried out by changing the inner controller gains to simulate a low-impedance robot with a deficient inner loop controller. In the image, experimental trajectories for the 2 algorithms are shown in green, and benchmark trajectories are shown in red. It is clearly visible that our skeleton method performs closer to its benchmark even with deficient inner loop control. In summary, the proposed skeleton-based algorithm achieves faster convergence with lower overshoot compared to traditional methods. It allows for configuration space control and is more robust to low-level controller deficiencies. Additionally, we do not require any markers to track our image features. Through our experiments, we have observed certain configuration singularities of our proposed representation. It is our belief that using intermediate reference configurations would overcome these singularities. However, we would like to study these further and determine effective solutions. We are interested in expanding our work to the spatial case and control the three-dimensional configuration of robots. To make this possible, we also plan to work on more robust skeletonization techniques and take inspiration from work done in the field of human body pose tracking. Applying our work to soft robots is of particular interest since our skeleton-based technique can effectively leverage the redundancy of such robots while maintaining robust control over these non-rigid systems that have complex dynamics. Thank you.